Okay, so one thing that has come up since last time or time before is a story I forgot to, well, I haven't told you about entropy, a way to sort of judge the entropy of a situation, which is to say the disorder of a situation. And so to tell you about it, the idea is this, that if you take a situation that basically the parts in the situation don't change. It's the story of, say, what's happening in a room. And if you take a series of photographs of that room over time, if no entropy was entering or leaving this room, it's sort of a thermally isolated system, its entropy will not go down. And in all likelihood, its entropy will go up. So the point of my story is that suppose you take that series of pictures, you drop the pictures on the floor, get them all scrambled, you know intuitively how to reorder the pictures for most situations. And I'll pick a situation or two shortly. I'll pick one to start with. There's a vase there, and a mechanism to knock the vase over, and you take a picture, click, the vase is all intact. The mechanism knocks the vase over, you take another picture, click, the vase is shattered. You take these two photographs, you drop them on the floor, you pick them up. In random order, you look at them and you go like, oh, I know which order these happened in. Which one happened first, which one happened second. You can give it to anybody else, they'll do the same thing. You know that the nicely ordered vase goes first, the disordered vase goes second. So you have an intuitive sense of entropy. You look at a series of photographs, you can put them in time order because you're essentially looking for the loss of order. And that's the breaking the vase is a pretty obvious one, but let me pick a different one that's not so obvious. Suppose the room contains dry air and a glass of water. Well, we don't, I should give away the secret. If you put that glass of water and the dry air in the room, close the door and start taking pictures, and you drop the pictures, pick them back up, you put them in time order because you know you expect the water to evaporate into the dry air, the cup will go relatively empty, maybe completely empty, and the room will fill up will become full of moist air. You know that's how things happen. And so you put them in time order. What you're saying is that first situation with the water in the glass and the dry air, that's an ordered situation. And as it drifts with time, it becomes more disordered by having the glass go empty or nearly empty and the room fill up with moist air. The entropy is indeed going up in that series. You know it, you know to expect it. And what you're expecting is basically the gradual accumulation of disorder. I've talked about the evaporation of water into dry air, that it continues, of course, until you hit 100% relative humidity. So if you've got a really big glass of water, a tub of water, it will evaporate and evaporate and evaporate, and it gets slower and slower, and it gets slower and slower according to my original story about the slowing process, which is that the landing and leaving process drift closer and closer to balance. And eventually, of course, they do balance. And interestingly enough, so according to the landing-leaving idea, you hit 100% relative humidity when water leaves the surface of the liquid water as often as it lands on the surface of the water. So there's no net transfer of water from the liquid form to the gaseous form. That was one story. The other story, in terms of thermodynamics and law of entropy, is that's the most random situation you can get. That's the most disordered. And if you have a full glass of water and dry air, that on the other hand is quite orderly. And so the water evaporates in order to make more disorder, to go more and more random, until finally, when the landing and leaving process match, and the water's at 100% relative humidity, you've hit maximum entropy. You can't do any better. In fact, if you put more water into the air, somehow or other, it will begin to condense. It'll come back into liquid water, because if you have way too much water in the air, that becomes orderly again. All right? So the point of this is that if you just think of the photographs, the series of photographs of a simple situation and put them in time order, what you're doing is you're ordering them from low entropy first to high entropy at the end. It's okay? It's Ben's birthday today. Happy birthday, Ben. All right. So, on to business. I finished up in a flurry last time, before I go to clocks, talking about gasoline and premium versus regular. Because if anyone would like to do that demonstration of compressing air, think about volunteering in a second. I'll ask for a volunteer to do it again. Here's the idea, that if gasoline ignites too easily, when you mix gasoline and air together, and you go through the compression stroke of an automobile engine, that fuel and air mixture is taken from room temperature and atmospheric pressure and density, and then shoved together very quickly to very high pressure, very high density, and the temperature surges upward because you're doing work on it. In the engine's doing work on it. That surge in temperature can ignite the fuel and air mixture. And if that happens, the piston cylinder knock or pre-ignite. The fuel and air mixture ignite without waiting for the spark plug. And they ignite it during the compression, which is not when the engine is positioned to make best use of that fuel and air mixture, the push from that. So modern cars are designed not to do this. And the way they avoid doing this in part is by not compressing the fuel and air mixture too hard, and by using fuels that are difficult to ignite. Believe it or not, they're engineered so that they're tough to get that initial that activation energy you need to get the reaction started is higher than it would be if they didn't engineer it that way. And so-called regular gasoline at the filling station is good enough for nearly all cars made at present. That fuel mixed with air, compressed in that engine, shouldn't knock. On occasion, it will knock in certain extreme situations. Knocking used to be more common because cars required careful tuning. The timing had to be controlled properly so the spark occurred at the right time. The fuel and air mixture had to be handled carefully so that it was uniform inside the cylinder and all that. But modern cars, there's a computer adjusting the timing all the time. The fuel air mixture is made more uniform than it used to be because they use fancy fuel injectors and all sorts of stuff. So basically, modern cars don't knock much. And as a result, ordinary regular gas, so-called 87 octane gas, is good enough. And the other grades, which they always tempt you to buy, and so this is my harangue again, what are they suitable for, apart from paying extra money? They're suitable for cars that have higher compression engines. And higher compression means that they take the fuel and air mixture and they pack it more tightly, and they hit a higher temperature during the compression stroke. What's the value of that? Minor increase in efficiency, perhaps, but not a lot. Actually, one of the main places in which premium gasoline can be important is with turbochargers. What's a turbocharger? A turbocharger is a device that compresses the air before it's put into the engine, so they can pack more air into the piston cylinder system during the induction stroke. And since you got more fuel and air in there, there's more energy available there. You can get more oomph out of the car, out of the engine. So the turbocharger takes an engine that's got a volume of maybe 2 liters of empty space and makes it behave as though it had 3 liters or 4 liters, because it's using the empty space more productively. It's putting more stuff in it. there's a downside of the turbocharging process, and that is if you compress the air, which they do with a turbine, you know, that's the origin of the word. If you compress the air before you send it in, you cause the air's temperature to rise, right? Because compressing the air necessarily increases its temperature. You're doing work on it. So they're putting heated air into the engine and then compressing it. So the final temperature is higher than it would have been if they didn't, in effect, preheat it. So actually, most turbocharged engines have a cooling section after the turbocharger, what at least was called an intercooler, that takes the turbocharger, makes the compressed air for the engine, they then cool the air back down to room temperature, and then they put it in. But without the intercooler, you might need premium gas. In all likelihood, you don't, okay? So save the money. Public service announcement. Does anyone want to do the demonstration of compressing air and having an object at the bottom burst into flames as a result? No? Okay, I'll do it then again. You guys are boring. All right, so here it is. So just piece of fluff. All right. Just make sure everybody knows what I'm doing. This is a closed cylinder made of plastic. They used to be made of glass, but once in a while they would burst because the pressure does surge up a lot, okay? So when I shove the plunger down, I'm going to take room temperature air at ordinary density and pressure, do a huge amount of work on it, and have its temperature just skyrocket up to like 1,000 degrees, which is enough to ignite that paper. Ready? Get set? Ta-da! All right. Yeah. Okay. Thank you. All right, so any other questions about heat engines, heat pumps, the world of thermodynamics, things that are on your mind over that? Happy birthday, Way, too. All right. Yeah, now I gotta have, you know, I can go get my balloons. Yeah, I won't. Clocks. So to shift topics now to dealing with clocks, at least until the advent of the cell phones, where now you're all carrying around basically a display that tells you what time it is, people at least used to walk around with a device that actually kept time itself. Your clock, your smartphone somewhat keeps time itself, but it's more of a display than it is a clock. But I still wear a clock. Some people still wear a clock. I guess, you know, when you make your I would say your first million, but maybe it's your first billion, you can go and buy the Philippe Petit clocks, watches that cost as much as a house. And when you do that, you start getting back to the real clock, which is a device that actually keeps time itself. And the way it keeps time is, in effect, they're very simple devices. They have a component inside that just ticks off a rhythm. It just marks maybe once a second, it marks every second. Tick, tick, tick. That's part one. Part two is a source of energy that keeps the ticking going. Because any mechanical or otherwise device that does this ticking process inevitably uses up energy, primarily because of imperfections. The reality of the world is there's friction, there's air resistance, there's various things that gradually sap the energy out of any mechanical system you can imagine. And so you need an energy source. And the third component, and then we're done, is a counter, some device that counts the ticks and displays them in a way that means something to you. And that's a clock. And the focus, my focus then is going to be on the ticker. You know, how do you make a device that ticks off the seconds, ticks off the hours, ticks off some unit of time? And what's sort of the physics of that? And it turns out we already have encountered these devices many times over the course of the semester. They're systems that oscillate about a stable equilibrium. They move back and forth about a stable equilibrium. So I don't know, what was one of the oldest ones of those we did? Oh, I don't know. I was doing marbles rolling in a ball in a bowl back and forth. A tricycle, you tip it, it goes back and forth. any of these things that has a stable equilibrium. So there's an arrangement where it can sit there with a minimum amount of total potential energy. That's a stable equilibrium. If you pull it away, it will tend to go back. So for example, just to pick one at complete random, this is a device that has a stable equilibrium, and if I pull it away from equilibrium, of course, forces or torques, in this case it's a force basically, arises that pushes it back towards equilibrium. And so it accelerates back toward equilibrium. And in those stable equilibrium systems, we've already noticed that just because you get to equilibrium, the thing gets to equilibrium, doesn't mean that it stops there. In fact, it typically coasts right on through. So just to sort of remind you of the story of one of these systems with a stable equilibrium, it typically has energy in two forms. It's almost always true. Two forms. One is in potential energy, one's kinetic energy, and the energy goes back and forth between those two forms. So for example, it's gravitational potential now, kinetic, gravitational, kinetic, gravitational, kinetic, and gravitational. It's going back and forth. The energy is shifting back and forth. What else about it? It has a weird arrangement of acceleration and velocity. They're out of sync with each other. Now the fact that this is going in an arc makes the acceleration a little complicated at the bottom, but basically it's accelerating back towards center particularly strongly now, and particularly strongly now, and right at the center is in effect a minimum of acceleration. Often it's a zero, but it's basically it's got maximum accelerations at the ends and maximum velocity at the equilibrium. So it's going back and forth, maximum speed. Yeah, so again, the fact that it has maximum speed at the middle at equilibrium is accompanied by maximum kinetic energy at equilibrium. But we've done this with questions on the old exams or homeworks, whatever. You throw your backpack on the bed and it bounces up and down and up and down. And when does it have the maximum speed, right? Equilibrium. When is it got the maximum upward acceleration? When it's at the bottom of the bounce and so on. You remember all these questions? The dreaded questions. And so we've got a timekeeper approximately. Now we want one other thing about this timekeeper, this ticking device. Well, it's got two things. Well, one thing. I just want to follow my current thought, and that is, if you think back to when I was talking, or beginning of the semester basically, about doing work, that you can add energy to this swing device, sort of in one of two extreme ways. Back then I was talking about it in the context of like pushing some kid on the swing. Remember, you can have the kid sitting there, you go, push me, push me, push me, and you go like, okay, I push you, there, okay. And one mighty shove did a whole lot of work in a hurry, and everything's in there, business, off you go. But it's more polite or friendly to get the kid swinging by giving them little pushes once per swing, approximately. And you always do it as they move away from you because you want to do positive work on it. If you push them away from you as they come toward you, you do negative work on them. You slow them down, right? So I told you early on that today that for clocks, in the timekeeper process, you want to keep adding energy to it to keep it going. And so it will be in this form, the little pushes sort of once per motion. It doesn't have to be once per motion, but it can be once every 10 motions, once every 1,000 motions. You just got to keep pushing. Okay? Now, to go back to the path I was about to talk about with a timekeeper like this, the other detail of timekeeper that you want for a clock is that you want it to tick at uniform intervals, no matter what. If it's going to tick once per second, you want it once per second regardless of gravity or moving around or how big the tick is. If it's ticking loudly or ticking softly, who cares? You just want the steady 1 second tick. How do you do that? Well, it turns out that if, and let me name something too. Let me give you a name. That the time it takes for this to tick, what do physicists call this? I'll call it, the tick will be from now to now. So the tick is something like 4.5 seconds. I've done this too many times, that's what I know. And that's called the period of the oscillation. Oscillation is a fancy word for this cyclic motion. So oscillation, vibration, they're almost interchangeable. So it's called an oscillation. And the time it takes to do a round trip, the full cycle of motion is called the period of the motion. There's another word that comes up in some contexts that if you look at how many times does it swing back and forth per unit of time, I would normally say how many times does it swing per second, but this is so slow that it might be how many times does it swing per hour. And that would be the concept or the physical quantity that would measure how many ticks or cycles per unit of time is called frequency. So frequency and period are reciprocals of one another. As the period gets longer, that is, it takes longer to do each swing, the frequency, that is how many swings it does per hour, goes down. So as period goes up, frequency goes down, and the product of the two is something interesting, but I leave it alone. Okay? So what we want is we want the period of the oscillation to be very uniform, and in particular, very uniform regardless of how big that motion is. There's also a name for that motion. The extent of the motion is just called amplitude. And these names, do I care whether you remember the names? No, but I'll tell you them anyway. So this is a small amplitude motion, and this is a big amplitude motion. And it turns out clocks that have a timekeeping device, one of these rhythmic cyclical things with a stable equilibrium, one of the hardest things for those clocks to control is the amplitude of the motion. It's hard to make sure that you keep this guy swinging exactly, say, 1 meter from center on each side. You're be there with a ruler trying to measure each time. Nah, it's too hard. So you want to make one of these oscillating systems that has a period that does not depend on the amplitude of the motion. That gives you a lot of room for messing up and still get a steady beat and a good clock. So are there systems with stable equilibria so there's rhythmic motion shows up and a period of oscillation that doesn't depend on amplitude? The answer is yes. And in fact, a lot of them do. And what leads to that behavior? It turns out that the influence that restores the object to its equilibrium, which is forces or the torques that restore it to equilibrium, all they have to do is be proportional to how far you are from equilibrium. So if this pendulum, when I take it away from equilibrium by 1 foot, I'll mix my units and who cares. For 1 foot, if the restoring force on it now is 1 pound, I'll stay in American units. And if I take it 2 feet away from center, from equilibrium, now the restoring force is 2 pounds, 3 feet, 3 pounds, 4 feet, 4 pounds. If you get that proportionality, you get an oscillator with a period that doesn't depend on how far you take it away from center. And that kind of oscillator that has a restoring force, technically, the restoring force is proportional to the displacement. Double the displacement, you get double the pushback. That's called a harmonic oscillator. And harmonic oscillators, just to finish the thought, is they are everywhere to good approximation. An awful lot of things are approximately harmonic oscillators, where approximately means that the restoring force might not be exactly proportional to the displacement, but it's pretty close. So they're everywhere, and they are the best understood physical system in nature. So physicists, they show up everywhere in physics, and physicists understand them very well, so that whenever you can identify a system as basically a harmonic oscillator, you get all this understanding comes along in a jiffy. This is a pretty good harmonic oscillator. Not perfect. Pendulum is close to a harmonic oscillator, close enough to be a great timekeeper for a clock. And here's the idea, that if I do take it one unit, this far away from center, it has gone up a small amount. And if you do the geometry and stuff like that, you discover that it's risen approximately, I don't know, let's say it moved up 1 inch. If I take it 2 feet from center, it will have moved up a 2nd inch. 3 feet from center, it will move up a 3rd inch. And as a result, the swing, the tendency for it to go back gets stronger and stronger. As it rises up here, it's a way of thinking about this is that when it's at center, it's as though it's moving on a flat surface. As it goes off center, it's as though it's moving on a tilted surface, on a ramp. And as it goes farther from center, it's more on that, the ramp gets steeper. Can you see the ramp getting steeper? Same thing here. The ramp gets steeper and steeper. In effect, it's moving in a round-bottomed bowl, circular-bottomed bowl. And so the restoring force does get stronger as you get away from center, and it's almost exactly proportional to how far it is away from center. By the time you get up to the catwalk with the thing, it's gone to pieces. It's a mess. But down here, it's great. Is that okay? So it is an example of a harmonic oscillator. It fits the requirement. Restoring force proportional to displacement. And when you get for, not magically, but for free with that situation is, you get this rhythmic motion that's independent, with a period that's independent of amplitude. If that's puzzling to you, just look at this. Watch. I will play timekeeper here, and we'll time 10 motions. The advantage of having my own watch, I actually have a timekeeper. You can do it on your cell phones if you like. I'll let it swing small amounts, 5 times. And I'll start when it comes over here. Start. 1, 2, 3. I'll do it 4. 4. Okay, so that took 18 seconds. Now, if I make it swing a lot, one, actually 2, 3, 4. Actually, I got to start with 0. It's the same. You know if I do this right, it's going to work out the same. Think before I do it. The first one is 0, not 1. Okay, so I stopped my clock too soon the second time. Anyway, the notion is this, that if it's swinging just a little, the forces are quite gentle. It has very little distance to travel through, but the forces causing the accelerations to make it go back and forth around equilibrium are wimpy. So it takes a long time to go through those motions anyway. If I take it far from center, then the forces become quite strong. And although it's got a big distance to travel, big amplitude, it can do it. It can get through those quickly enough that it has the same rhythm as before. So that's all my only point with that all. And so this guy ticks, it's something like 4.5 seconds. I've done it often enough, if I count correctly. Where does that come from? Where's the 4.5 seconds come from? Well, it turns out any harmonic oscillator has sort of 2 parts fighting it out. One is that restoring influence, pushing it back towards center. And the other is an inertial influence trying to have the thing go in a straight line at a steady pace forever. And so they're fighting each other. The bowling ball in this case wants to keep going forever. The restoring influence pulls it back, slows it to a stop, gets it to actually start speeding up toward the center. It comes roaring through equilibrium, and inertia now carries it off in the other direction. The restoring influence begins to pull it back again. So you can increase, just to pick a direction, you can increase the period, make it take longer by cranking up the inertia. It typically use more mass, make it harder to get that attention of that moving object. So you can make the period longer with more mass or a wimpier restoring force. If you've got a wimpier restoring force, it takes longer for this wimpy restoring force to say, please come back. So let me start, well, I'm going to pop these off for a second. Lots of different pendula to play with. Another example, in fact, sort of the prototypical example of a harmonic oscillator is a mass on a spring. The mass is the inertial part. The spring is the restoring influence. And springs, as we talked about back in the days of weighing things, spring scales, springs exert restoring influences that are proportional to how far you stretched them or compressed them or bent them. They're perfect. They're perfectly matched harmonic oscillators. So this is like the classic harmonic oscillator, a mass on a spring. And as a result, it has a period, bounce, 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 that doesn't depend on how big the bounce is. Bounce, bounce, bounce. It's the same. I won't count it. It's too dorky. Okay? And if you want to, gravity appears to be involved in this because gravity shifts the equilibrium down, but basically the bounce is unrelated to gravity. Gravity is just a nuisance that makes this, obscures the simplicity here. It's bouncing about this equilibrium. Ooh, where is it? About there. If there were no gravity, it would be bouncing about this equilibrium up here. That's the only effect. If I increase the mass, so this is a 200 gram mass, if I go to 500, this will shift the equilibrium down because of gravity, sorry, it just drops down to there. But now it's going to have a slower period. Bounce, 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 because the spring's the same as it was, but the mass is more resistant to acceleration. Getting its attention is harder. On the other hand, if I go to a little teeny mass here, bounce, 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 you know, okay? Easy to get its attention. So the increasing the mass, doing nothing else, clearly slows down the period, longer period. On the other hand, this is a stiffer spring. If I put the 500 back on this guy, bounce, 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 bounce. Don't swing, that's pendulum land. Okay? The spring is now stiffer. It fights harder and says, okay, I don't care, you're a 500 gram mass, big deal, I'm tough. I'll shove you through your motion just as fast. The little guy, this guy should go like crazy. Boing, 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 boing. Okay? So it's a balance between the inertial thing and the stiffness of the restoring force. Any questions about the way that comes off? Now I could ask this as a question, but I'm not going to do it. With the pendulum, the restoring force, first of all, the restoring force depends on two things. I'm not going to change the mass of the ball right now. The restoring force depends on two things. What are they? They are how long the pendulum is. As the pendulum gets longer, getting a foot away from center becomes less interesting. You know, it has less of an effect. If I take, in fact, let me go over to the other pendulums, just so I've got something. This is the short one. I'll put them up front. This is the long one. I'll put it back. And this is the medium one. Okay. This guy, if I take it, I'm not going to go a foot off center, it barely goes up at all. And as a result, the restoring force that shows up, it's on a ramp that hasn't gotten very steep. So this is a gentle restoring force for a 1 foot displacement. Whereas this guy, you take it a foot away, whoa, it's way out here. The restoring force showed up much faster. So the point is that the longer the pendulum is, the weaker the restoring force. Shorter the pendulum, the stronger the restoring force. So this is like it's like on a stiff spring. So this guy goes through its motions fast. This guy goes through its motions slowly. Up, naturally. Oh, you, trouble. Yeah, it's good enough. Okay, this is much slower. And actually, it's got a mind of its own. Here, come on out here. There you go. This pendulum is a 1 second pendulum. It takes 1 second to go through its full motion. It's pretty close to 1 second. This guy is a 2 second pendulum. And they differ in length by a factor of 4. So why the factor of 2 in period? There's a square root around in the mathematics. So a quarter meter, this is a quarter of a meter long, almost exactly. And a quarter meter pendulum, almost approximately, it's an approximation, is a 1 second pendulum. A full meter is a 2 second pendulum. Back in the day when they would have wall clocks, or basically household clocks that used pendulums as their timekeepers, the ones on the wall would usually, because they're not, you don't want a gigantic thing, you want a little thing, so you use a 1 second pendulum that's about a quarter meter long. And for like a grandfather clock where you got some room to move, you go for a 2 second pendulum. And so the counting mechanism, what does the counting mechanism do? It just counts, if it's got a 2 second pendulum like that, like a grandfather clock, you advance the hands 2 seconds every time it ticks. And you just mechanically count the seconds off from whenever somebody set the clock. Okay? Questions? All right. So adjusting the length of the pendulum adjusts its period. The longer, the slower. That pendulum has a period about 4.5 seconds because of its great length. If you made it taller still, it would go even slower. You all okay with that so far? What's the other feature that adjusts the period of the pendulum? Turns out it's the strength of gravity. And the pendulum is an unusual harmonic oscillator. And how do I want to do that? The pendulum has a mass which by itself would, changing the mass of the pendulum by itself and doing nothing else would slow down or speed up the period. That is, if you went to a much more massive pendulum bob, in concept, and did nothing else, and nothing else happened, cranking up the mass of the pendulum bob would cause it to go more slowly, longer period. Is that okay? It was like me playing with the spring and the mass. So as I went to bigger masses, it went slower. There's a problem though, and that is that if you increase the mass of the pendulum bob, you also increase the weight of the pendulum bob. You can't help it, right? Because every kilogram here on the surface of the Earth develops 9.8 newtons of weight. So if I crank up the pendulum bob, go to a great big bowling ball, wrecking ball, okay? Then I get more mass, which should slow things down, but I also get more weight, which speeds things up. Because remember, weight is involved in this restoring force. Believe it or not. If I turned off gravity, I could put this ball out there and let go of it and it would sit there forever, right? The weight of the ball is entwined in the restoring influence. So a pendulum is an unusual harmonic oscillator where changing the mass of the pendulum bob doesn't affect its period, because you cannot change the mass without also changing the restoring force. And more mass gives you more restoring force, which perfectly cancels the increase in mass. Is that okay? Most harmonic oscillators don't do that. If you increase the mass, it goes slower, because the restoring force doesn't have anything to do with the mass you increased. This one's unusual because it does. Okay? So pendulum clocks were probably the earliest of the classic clocks, of the clocks that didn't involve like filling a water basin or burning a candle. that had a timekeeper that ticked. And so pendulum clocks, they work very nicely. The duration of the time it takes to do the tick, the period of the tick, depends on the length. And one other thing, and that is the strength of gravity. If we were able to double the strength of gravity here, just by some crazy miracle, whatever, that pendulum would go faster. Why? Because now, without changing its mass, we stiffen the restoring force. We got more, turning up gravity causes it to be pushed back towards center more aggressively, and it'll go faster. So this pendulum, it takes 4.5 seconds to go through its period. If you took it to Jupiter, where gravity is like 2 or 3 times as strong, it would run it wouldn't take 4.5 seconds. It would be more like 2 or 3. It would go faster. You okay with that idea still? Well, that actually is an issue on Earth. Gravity here on Earth is pretty nearly constant, but not perfectly constant. So what it meant is that pendulum clocks, when they arrive at your location, you actually have to adjust them, because even though the manufacturer had it ticking off time exactly as the manufacturer wanted, your local gravity might be a little stronger, a little weaker, and you have to adjust for that. So here's my pendulum clock. The energy source, which is on the floor here, is a weight, and the act of lifting this weight up, which I'm about to do, will invest energy into the system. I'm doing work on it, right? Now the energy's there in gravitational potential energy. And that energy will be used to keep the pendulum swinging once I get the pendulum started. So there it goes. Okay, so it's being given little teeny pushes with energy derived from that weight, which will descend gradually over the period of it takes about a week for it to hit the floor. And that pendulum is now just going to tick back and forth for the rest of the class. And the rest of the mechanism here is a counting mechanism. It just advances the hands the right amount, properly adapted to the tick rate. Is that okay? But to get this to tick at the right rate for these particular set of hands and gears, you have to adjust the pendulum's length a little bit. And so the pendulum, I'll stop it for a second. The pendulum has a little screw thread at the bottom and a nut on it that you can move up or down the screw thread to change the effective length of the pendulum a little teeny bit to get it to swing at just the right rate. So if you get a pendulum clock like this and you're compulsive, you have to spend a couple of days adjusting it to get it right on. Is that okay? So that's the first of the classic timekeepers. The second of the classic timekeepers is a response to some problems the pendulum clock has. One of them being that you have to adjust it for its location, which is kind of a nuisance. And the other is you can't move it once it's working. I mean, you can move it and then from here to there and then start it again, that's okay. But you can't wear it on your wrist, for example, or drive around with it. And so people went looking for a harmonic oscillator it's essentially immune to gravity, that is oblivious to gravity. So don't use gravity as part of the restoring force. Get weight out of the story. And the other thing is try to get it so that gravity doesn't cause trouble, like as you tip it and stuff. So it doesn't exert any influences on the timekeeper that would mess up its ability to work right. And the solution that people came up with, not quite close, the solution that people came up with was a torsional disc or ring. And so the idea of a harmonic oscillator, you just need an inertial type thing, and you need a restoring influence that's proportional to the displacement. Nobody said it had to the movement had to be in a straight line. It could be a rotational thing. So this is an example of a rotational harmonic oscillator, or a torsional harmonic oscillator. It has a stiff rod here that is fighting to orient this disc, and the disc has rotational mass, of course, to orient the disc like this, with that yellow stripe pointing off in that direction. If I displace the disc from that orientation, I'm twisting the rod, which hates it. and it's pushing, it's twisting back. Say, no, 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 I want you back in this location. This is equilibrium. It's a rotational equilibrium. Okay? And the twist back is almost exactly proportional to how far it's displaced in angle away from equilibrium. And as a result, that oscillation back and forth, rotationally, is almost perfectly independent of how big the amplitude is. This is a little amplitude. Let me go for big amplitude. There's big. Same time. Tick, 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 tick. Okay? So what people managed to design and engineer is little rings that would go back and forth. They're like a little wheel. It's like a little bicycle wheel. Doot, 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 doot. And it would be twisted back and forth by a very gentle spring. And it was actually a coil spring. And I'll show you that. I've got one, you know, these watches are still available. And these are the watches of my growing up. So I used to have them. They weren't perfectly good. They were good enough. Where is it? Document. Camera. There you go. There, you're looking down on the watch, and it's not running right now, which is good. That was the point. The ring is here. This wheel, it's partly hidden. There's a piece of it there. There's the top. It's turning on a bearing that has that little ruby there. The ruby is jewels are actually part of the bearing. Let me wind it now so it'll get moving. There it goes. You see the ring rocking back and forth? It's just like this, that torsional ring. And because its center of gravity of that ring is right in the center of the ring, right on the axle, gravity doesn't affect this thing. The only thing that really affects it is the spring, which you can't see. It's a tiny coil spring. It's hair thin that is exerting the restoring torque to keep it back on center. So it's rocking back and forth with a period that's determined only by its rotational mass and how stiff that spring is. And probably there's an adjustment. Most of these things will have somewhere an adjustment. This is modern El Cheapo ring balance. It's called a ring balance clock. Let me show you an older one from like a couple hundred years old here. There is the torsional balance on top of this carriage clock. And if I planned ahead and pulled out the winding mechanism, you can see the adjustment there where it says S and F, and it's covering over F. That changes the spring a little bit and allows you to adjust this clock so that it keeps better time. And now I'm going to wind it. And to get the ring started, you get a little jerk, okay? Just to get it off center so the mechanism begins to feed energy to it. And there it goes. And you can see the spring a little bit. It's that coil of hair, hair thin coil. So it's rocking back and forth, and the rest of the mechanism there is just counting. Just counts the cycles back and forth. All right? The last kind of clock worth talking about, another harmonic oscillator. We talk about why these have issues of accuracy. The next kind of clock is a solid piece of material. Quartz clocks, where I'm heading is to a quartz clock. The way a quartz clock works is it takes advantage of the fact that if you just have a solid piece of material, it actually has spring and mass issues of its own. It has two ends and a middle. And the two ends, if they happen to be heading apart from each other, they stretch the middle and it fights to pull them back. Or if they happen to be heading away from each other, or toward each other, the middle gets compressed and fights to push them back. Basically, it's got an equilibrium length, and it can oscillate about that equilibrium length, and it makes a nice harmonic oscillator. The question is whether I can get it to go. Never very good at this. Now, there's the cheater's method. There you go. And that pitch, you hear it as a frequency rather than as a period. The period's very short. Maybe a 200th of a second. I don't know what this. Anyway, that's the whole thing getting longer, shorter, bouncing back and forth about equilibrium. And quartz clock, I'll leave it for next time. A quartz clock is using that kind of motion as its timekeeper, and it gets tremendous accuracy out of it because of the nature of quartz, and that particular motion is so resilient against trouble. Okay, so we'll finish up on Monday if you're here.